the what and when and how much of the functional coverage. Up to 80% of the overall design cycle time can today be spent on verification. Constraint random testing (CRT) was developed in response to greatly reduce the amount of code needed to create a verification environment. However, CRT-based methodology do not include functional coverage analogous to shooting blind. Functional coverage provides essential feedback for knowing what was tested, the device configuration used, and perhaps most important, what still has not been tested. It is thus indispensable to answering the fundamental verification question: are we done yet? We must remember it is a feedback mechanism only. However, that feedback does allow verification to be focused on incompletely tested area. Coverage-driven verification. Coverage-driven verification (CVD) is a natural complement to constraint random testing. It is important to understand the different types of coverage that can be used in verification and total coverage analysis. Functional coverage. Functional coverage is one of the facets of a total coverage analysis methodology that includes assertions and code coverage. Each helps determine, are we done yet? It focuses on the actual functionality of the design and is closely tied to its specification. Some facet of the functionality will be must behave, other will be nice to behave. A properly executed functional coverage plan will identify this and can be useful in getting a design for tape-out. In this case, 100% of the must-haves will be exercised, but perhaps only 85% of the nice-to-have. Code coverage. Code coverage answers different questions. Have all the code been exercised? As said, nothing of the correctness of the code, nor can it address unimplemented functionality. It does provide a measure of the completeness of the testing. Any unexercised code either has not been stimulated during verification or is redundant. Functional and code coverage are complementary, since both help reveal holes in verification. Assertion coverage. Ideally, designers embed assertion in RTL code to specify its function and monitor for out-of-bound operations. For example, an arbiter may be specified to only offset 3 simultaneous transactions. Assertions can be coded to flag an error or warning if this limit is exceeded. Functional coverage goals. Coverage goals depends on the type of coverage, and the figures may be different in each case. It may be possible to achieve 100% code coverage, but less than 100% functional coverage. This is because code coverage cannot tell us anything about unimplemented functionality. By definition, functional coverage can. There is no definitive way to setting coverage goals. The target may be 80%, 90%, or 100%. But what do these figures actually represent? The real goal is confidence that the functionality is correct. It is usually a combination of number of test runs, bug discovery rate, DUT stability, marketing, that is, schedule. It is our experience that this last factor often determines when a chip is ready to ship. With well-defined coverage goal, at least it is possible to assess the risk of taping out early. The three functional coverage questions. The coverage plan is central in the verification plan in a CDV approach and leads to the three fundamental questions of the functional coverage: what, when, and how much. With a careful consideration, you will get data overload. If you dread reading your coverage report, you have a problem. What to cover? The first consideration in creating a functional coverage plan is determining what should be covered. There are several different kinds of objects for which functional coverage is appropriate. A useful source of what to cover is obviously the design specification. Others can include system specification, interface specification, standard protocol specification, on-chip protocol specification, design specification, design engineers for embedded items. For the functional items themselves, these include any interesting event of scenarios, basic functionality, state machine, and protocol, both embedded and external. A consideration of where to sample can help determine what to sample. Boundaries between the different levels of abstraction are appropriate places to look for data items to sample. For example, applying a frame of data to a system that breaks the frame into packets to send to one part of an SoC. Here, we have the frame boundary and packet level abstraction. The packets themselves may be decomposed into lower level objects. Our test environment may be composed of the transaction level models that convert one level of abstraction to another. TLMs often include an analysis port that observe the appropriate transactions as they flow through the model. Such ports provide a nature interface to the coverage model. If there are any corner cases in the design, these should also be covered. Examples include FIFOs of the buffer occupancy levels become full and empty, and etc. In a CRT-based environment, the configuration of the device under test itself may be randomly generated. The configuration will also need to be covered to ensure that all legal modes of operation has been used. A consideration in what to sample is to ensure the sampled items are interesting. For example, a datacom's packets may have a cyclic redundancy check. The CRC's value does not reveal any interesting information since it is a computed number, but its validity is relevant. When to sample. Appropriate timing when to sample coverage data is the key to avoiding data overload. Engineers who are new to a CDV methodology often oversample, typically using the system clock as the event to trigger coverage. It's important to use correct granularity not only to minimize the data collected, but also to maximize its information content. If a state machine is being covered, it is more interesting to sample on state changes rather than at every clock edge. When deciding what to sample, we look at where to sample. This also helps determine when to sample. Abstraction level boundaries use much closer event than the clock. For example, a single event when a whole frame of data is applied to a device, whereas many events are emitted each time a packet is transferred to a transducer. TLM analysis ports may already include the appropriate event for sampling, as well as dynamic runtime coverage. If we are randomizing device configuration, we need to sample coverage after randomization. Such device configurations may use a configuration object which is generated before a simulation start, but which is transjected into the DUT to set the mode of operation. Another consideration is to ensure that data is valid when it is sampled and there are no race conditions present. How much to sample? Figure 1, using the cover point binge construct. How much to sample? The key to using the coverage successfully is to minimize the data collected, but to maximize its information content. Functionally equivalent to sampled. In many cases, individual data values have no functional significance. For example, the payload bytes of a packet may have no functional impact on the operation of the DUT beyond a couple of specific values. Values that are significant can have their own groups, and all the rest can be lumped together into bins. This greatly reduces the data to process. The example in figure 1, page 20, shows P20 shows how the cover point binge construct can be used. There are also options to ignore certain values and to specify illegal values. It's better to have explicit monitors for any illegal state of values though. Cross coverage. Another source of excess data is blindly sampling items that are not interesting. For example, if a router is being verified, one of the coverage items may be the different type of packet, for example, small, large, headless, and tailless, and etc. If the coverage is only performed on packet type, then a large volume of data is collected. Of greater interest is to see what type of packet comes out of which output port. This example of cross coverage usually reveals more about the operation of the DUT than the individual items. Figure 3. Packet sizes grouped into 3 categorized and a cross made with the destination port. In Figure 2, packet sizes have been grouped into 3 categorized and a cross made with a destination port. Grouping the packet sizes into 3 bins reduces the cross product from 128 times 16 to a more manageable 3 times 16. For cross coverage, the contribution of each item and cross to the overall coverage goal should be considered. By default, all cover points and crosses have the same weight. This can lead to unrealistically high overall coverage grade. The weight of the individual item should be set to 0. Conditionally sampling, an important consideration in coverage sampling, is to ensure that data is relevant. For example, not sampling DUT output during the reset or configuration phase. System Verilog's coverage model allows very fine-grained control of the conditional enabling of the data capture, as Figure 3 shows. Figure 3, fine-grained control of conditional enabling of data capture with the system Verilog. Transition coverage. This allows sequences of change of the value to be sampled. Figure P21 shows a state machine, but transaction coverage can be used for any sequence operation. For example, verifying that every configuration register has had a read and write read test performed. Architecting coverage in System Verilog. In a CDCRT methodology, coverage is essential, not an afterthought. It's crucial to incorporate it in a flex, reusable, and controllable manner. CRT is class-centric, so it makes sense to take advantage of this when implementing coverage. Figure 4, State Machine. The class-based cover groups as effectively user-defined types can be embedded in classes. This provides an encapsulation of the coverage model. A consideration for dynamic data object is whether we really want each object to have its own coverage group, as we are interested in the statistics of the object themselves. It may be more appropriate to use a single cover group to collect the information have the dynamic object, called the sample method of the single group when appropriate. A more flexible approach used in the mental graphics advanced verification methodology embeds a cover group and a derivative of an AVM underscore subscriber. This offers a flexible user interface and the means to attach an analysis port. Figure 5 shows the skeleton of this approach. Control issues. The embedded cover group in Figure 5 is shown without a sampling event. The only way to trigger coverage is to use the group's sample method. This is extremely flexible since the user controls exactly when coverage is sampled. Whether a sampling event is used or not, a group's sample function can be used to trigger coverage at any arbitrary point in time. Figure 1, embedding a group, I think that is figure 6. So in a derivative an AVM subscriber with mental graphics advanced verification methodology. The summary. System Verilog has a powerful coverage feature that allows the implementation of a coverage-driven constraint random test environment. We have demonstrated techniques to determine what, when, and how much of the coverage sampling using the System Verilog so that the functional question of verification, are we done yet, can be answered with confidence. Reference. It's quite old. Yes, quite old articles. Thank you.